Click it twice.
Okay, hi, David Chester. We have
Hello?
been collaborating on and off for many years, since 2008. I know you since 2018, right? Um, we haven't collaborated closely, but I've often talked to you, and it was always quite inspirational. Um, it's always good to brainstorm with you because you know so many things about so many areas of physics. You're like an encyclopedia, very helpful. Um, Recently I've been doing a lot of experiments on composition dependent gravity, and I heard you sometimes look into that, like non-Newtonian gravity, um, a little bit.
I mean, I don't look into it too much, to be honest. I mean, I guess I stay aware a little bit of what's going on, but I've been more interested in I guess metric affine gravity, basically gauge gravity approaches to generalizing general relativity. But yeah, I mean, I'm generally just trying to scope out all the different gravitational theories in general to try to understand what's possible.
Mm,
But yeah, there's been a lot of excitement with MOND lately. There's
mm.
been a fierce debate whether there's evidence for it or not.
I mean, with
That's been
those,
kind of happening.
I think it was neutron stars, right?
Yeah, to be honest, I haven't even looked into the details. I just know that there's been two
Yeah.
papers that came out that claim that MOND was acceptable, and then there was this other paper claiming that it wasn't acceptable to like 18 sigma,
Mm.
which is pretty large. So a little surprising it'd be that large. So I don't know. Yeah, there's some people now claiming that maybe that's actually support for MON, depending on how they calibrated their data. But yeah, I haven't really looked into it enough detail to
Mm.
have a
Yeah,
strong
but
opinion for myself.
theories like MOND um, are depending on a randomly set value of how gravity should be deviating from the norm. And so my theory is more fundamental because it goes on, it can't be adjusted. It's like only we say that gravity depends on the baryon count, and then the effect size you would expect for that, you can't change it. It's like for some elements it's 1/1000th of a difference, and then when you go to beryllium it's like 1/200th of a difference. So there's no room for calibrating. Okay, Fishbach does calibrating. He has a coupling constant, and so he makes these differences very small. Instead of 1/1000th, still it goes to 1 billionth. So because
Yeah.
looking only at one experiment, the Advis experiment in 1922, which was which is using a balance, and I think a balance doesn't really measure. It doesn't measure differences in acceleration, in Earth acceleration. In different heights, the balance will show the same. So I think it's very doubtful that it can be used to test the equivalence principle.
Mm,
First, I
interesting.
also thought that this would be the same with a pendulum, but actually a pendulum acts differently in different elevations. So so I guess I was wrong on that. It can actually be used to test the equivalence principle. And a guy
Well,
called
with
Giorgio
the,
Toro.
I mean, yeah, with the pendulum, I guess the resonant frequency depends on the strength of gravity, like little g, right?
Yeah, I mean, at first I thought maybe it will be a mixture because the pendulum is hanging down from something, and so maybe the force of that will maybe the g value, the small g value will be a mix of the string and the bob and the ceiling. But then I looked at the data collected by Giorgio Toro, and it was a surprisingly good agreement. He had four elements, and the hierarchy was exactly as I predict. And the difference between the materials was like a 99.97% agreement to 99.99% agreement, so pretty good. But he didn't know what effect size to expect, and so he's not a theoretician. He doesn't know much of theoretical physics. He just does experiments, and very good experiments over long periods of time. So for him, it was unimpressive because 1/1000th of a difference is not so big.
Right.
And so
Okay.
his paper actually has the title Shape and Inertia, because he saw bigger differences with shape, which is strange because he did it in a vacuum. So, and he's a bit frustrated that nobody comments much on the shape thing. Yeah, I don't know
Okay.
if
Yeah.
you have any idea on that. It's
I mean, yeah,
difficult.
it's hard to know. I mean, it gets to a point where it's just like, have I done the experiments myself? And then do I believe what, if not, then I have to kind of just believe what other people wrote to some degree, trust their analyses.
The very
And
believable thing about him is that he didn't know at all what to expect. So, so his
yeah,
numbers can't be falsified
yeah.
at all.
And I mean, I think in most cases, people don't try to make stuff up really. I don't think it's that common. I mean, maybe in some cases, but
File draw effect.
I mean, I think overall with a lot of this stuff, usually, I mean, I see where you're coming from. I think there's a chance that you're onto something. I'm not sure, but a lot of times it relates to like error analysis. So even determining the gravitational coupling constant, like the big G, determining that experimentally with low error is actually somewhat difficult, and so that's always
I believe that Gundlach in 2000 and Lohr in 2018, they did it extremely precisely. Their standard deviations are 0.00004 zeros and then a number.
yeah.
Yeah. So if you take those two together, then it's 4 zeros and 22. And so I'm using that for stainless steel. Yeah. And yeah, I think it can be very precise if you know that you should only look at one material and not mix them. These are the spheres that I'm using. I
Okay.
have some washers here made of steel, but but on the magnet they hang only on one side. I don't know if it's visible from here. So when I hang it, it kind of swings around. Yeah.
Mhm.
So maybe it would be better if it's if it's only a dot washer and not another ring, because at the end it's just on one corner of the ring. So I'm
So
gonna change that a bit.
you have that connected to a magnet, and so what experiment are you running? You're just like letting that drop to the floor or something, and then computing the time, or
Yeah, here's the timer. Took it. So then I drop it to this is the it drops on this platform. Well, I'm
I'll
on a
trust that there's
computer,
something on the
so
floor. Yeah. Okay.
yeah. If I was on a mobile phone, a phone would be easier. Now I dropped the timer. It says 0.6392 seconds. Yeah, well, I have many hours of video on that.
Yeah. So you're putting different materials in essentially plastic balls with a little metal ring around it, and
Yeah,
then
and I make sure that the one that, because they can't be exactly the same mass, because that would require infinite precision. So I make the one that's supposed to drop faster, I make it ever so slightly lighter, so that nobody can say, oh, maybe it dropped faster because it's heavier. So that argument is then impossible to make.
okay. Yeah, it is interesting. I mean, I think it is worthwhile for someone to explore it more and collect as much data as possible and
Yeah.
share it with the world.
And about the file draw effect, I mean, if you make a single video with 10 trials, then if there are enough trials in one video, then there's no file draw effect. Applies to many experiments in parapsychology too. If you have one if already one experiment has so much data that the chance against odds is very small, then yeah, then one experiment is already enough, basically.
Sorry, what was the effect you're referring to there?
File drawer effect, like when the effect is not large enough, then you just
Okay.
kind of ignore the data.
I see. So, yeah, what are next steps for you in your lab?
Basically, this is already very satisfying. I have the average difference in the average is 0.3 milliseconds, which is exactly what I predict. And the difference in the minimal value is also 0.3 milliseconds. But it's good to have non-overlapping standard deviations. And for the average, they're almost non-overlapping. And I see that the standard deviations are getting smaller. Unless there's some unlucky event, they might expand a little bit again, but only a tiny bit and then shrink again. So I guess if I do like 30 trials, then I guess the standard deviations might not overlap anymore. Actually, if I extend this to 3 meters, now it's 2 meters. If I extend it to 3 meters, they would already be non-overlapping standard deviations. But one could argue that with this free fall adapter, it can only delay and not be too quick. So one should take the minimal value, same as with the clamp that I used before. But now this magnetic free fall adapter is already so precise that that you can already almost use the average. Yeah. Normally the mode should and the average should align in order for somebody to use the average. Because if the mode is close to the minimal value, then it means the data is skewed towards the minimum. And I don't know how to do standard deviations for a minimum. One approach would be to list the current minimum, which will be the same for a long time, and then it might change, and then do the standard deviations of that. But it's not something that people usually do.
Yeah. Well, yeah. So, I mean, I think for you, the main thing is I mean, you have this hypothesis and you almost want to compare it to like a null hypothesis and then try to figure out how you could do it starting with one material, but then there should be a way to combine it across all materials. But
yeah, I have beryllium and phosphorus. The beryllium was not quite as heavy as the phosphorus, so I put some paper and some glue around it. So now the surface area is not exactly the same, but well, it's as perfect as I can do it here. Yeah.
But what I was getting to is that you want to get some number, like how many significant figures is it away? How many standard deviations away from the norm is the data you're collecting from that null hypothesis? So usually like a scientific discovery, usually they'll say like 5 sigma or something. And so it's like
sigma value.
basically, so yeah, like once you go one standard deviation, if you're away from one standard deviation, it's like kind of like maybe like a 33% chance, like 2 standard deviations, maybe like 95% chance.
For my analysis of all the G values ever measured for the last 200 years, there I believe the chance that it's a coincidence, according to my calculation, is like a 1 in 10 to the power of 18 chance. So it's well beyond sigma 5. You might want to check that. I mean, this is about my own experiments now. Yeah, but if I analyze the experiments of others, then I'm already far beyond sigma 5.
Yeah. Okay, yeah, that's just yeah, that's just a way to communicate in a way that others might be able to quickly understand.
Yeah, I mean, I removed some outliners, extreme outliners, which are nonsensical. Like instead, the reasonable value should be 6.6. Start with 6.6. Like if something is 6.7, it's just a nonsensical value. And these nonsensical values usually appear only when somebody is trying to measure G values mountains or huge lakes or something, then it seems it doesn't work. It seems to always be skewed to large values, which I think is just because of they can't. It's too contaminated. And in my own experiments, where I tried to measure G with the Cavendish experiment, when my air isolation was not good enough, the oscillation was too big, and so basically it was always too large G values.
Mm.
Okay. Yeah.
Yeah, that's interesting.
Mm. Okay.
So you're doing a
I hope
little,
we can collaborate more in the future, because we did a lot of collaboration some years ago for a few years, and lately not so much anymore. Yeah.
yeah, unfortunately, I'm
Revived a
pretty
little bit.
busy. I'm still finishing up ideas I've had from 2015.
Hmm.
So it's just a lot of stuff going on. But
Reminds me
yeah,
of myself when I had a break from physics. Okay, you didn't have a break, but anyway, when I had a break, I went back to all my writings from 2005, 2004, 2005, and yeah, tried to sum it all up. Yeah. Sometimes it's amazing how I used an idea from 2000, I think 2004. I used it this year and had a big breakthrough in predicting the muon and the tau mass, where I got 99.998% agreement, something like that. Yeah, I did a lot of. You said before that I was lacking a little bit in the particle physics area. I'm doing mostly cosmology and gravity, but now my particle physics is better too now. Okay.
very cool.
Mm, okay. Thanks for your time.
Awesome. Yeah, best of luck with your endeavors.
Yeah, and let's repeat that sometime later.
Sounds good.
Okay. See you. Bye bye.
Awesome. Take it easy.